Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series, where it is a party today. And we have our music here for the first time, so thank you very much, Paul, for that. Now, in just a minute, I'll be thrilled to roll out this week's episode with our very special guest, Campbell McLauchlan from the University of Cambridge. Before we get to that, as is our tradition, folks, please let us know where you're tuning in from today. And you can do that in the comment chat box here on YouTube, located somewhere above, below, left or right. You know where to find it on your screen. And that is the same place where we can keep this live and interactive, and you can ask questions of Campbell and myself during the talk, and you can discuss among each other, answer each other's questions. We always like to see it very lively. Now, folks, before we dive into that, we have one of our favorite questions, which is, where's everybody tuning in from today? So put that in. And before we get to the delay between you and me because of the speed of light and all of the other things, we have a small announcement, which I'm personally very, very excited about, because I had such a pleasure preparing several hours of lectures and seeing 6,000 plus students joining for the Qiskit Global Summer School this year. That was really a wonderful event. I met so many of you and had such a great time. And great news, the Qiskit Summer School videos are coming out September 18th on YouTube. So you can find them right here on this channel. So don't forget to click like and subscribe to know when that's coming up. I know a lot of folks have been asking me about those, so that's why we're thrilled to share that with you. Today, I see we have folks from New York, myself, Bolivia, San Diego, Iowa, Israel, India, Milwaukee, Wisconsin, Yokohama, Poland, Thailand, and many more locations. So thank you, everyone, for making the very diverse time zones. This seminar takes place every Friday at noon Eastern Time on the Qiskit YouTube channel. And the recording will be here after this talk, so you can always go back and rewatch it, but you can only ask questions live during the series. So with that, I think it's time we get started. I am your host, Zlatko Minev from IBM Quantum Research. And in this episode 134, I have the pleasure and privilege of introducing you to our producer, Paul, and to our very special guest, Campbell McLauchlan from the University of Cambridge. Hello, Campbell. How are you today?
I'm very well. Thanks, Zlatko. It's very exciting to be here. Thanks for having me on.
I know. We were looking up your 5-star rated Apple podcast right before this. So we're glad to have you here and to start with a bit of a pedagogic introduction to this interesting topic for us. Where are you yourself tuning in from today, Campbell?
So I'm currently at my office in the University of Cambridge. I figured this was a good place to come for a bit of peace and quiet.
All right, very fitting for the work you'll tell us about. Before you dive in, Campbell is a PhD student studying theoretical physics at the University of Cambridge. That's the one in the real Cambridge. After completing his Bachelor of Science at the University of Sydney, Campbell went to Cambridge, and in his PhD, working at the Center for Quantum Information and Foundations, Campbell studies quantum computing, information, and condensed matter physics. Beyond that, Campbell has an interesting side job or effort or hobby. I'm not sure what to call it, but Campbell writes for the... Yes, please do pop in.
Sorry, go ahead.
Campbell writes for the online publication of Physics World and produces videos and a podcast with the purpose of communicating ideas from physics to the general audience. And with that, Campbell, the stage is yours.
Okay. Yeah, well, thank you for that introduction. So today I'm going to be talking about some research I did and put on the archive a few months ago. So I'm going to be talking about, as the title suggests, twists on the Majorana surface code and bosonic and fermionic defects for fault-tolerant quantum computation. So I'm hoping that after the end of the seminar, all of those words will make sense to you. And this is work done in collaboration with my supervisor, Benjamin Berry. So yes, I will jump into it. So what I'm going to be talking about is how you can sort of, or some new methods for computing with the Majorana surface code. And to talk about the Majorana service code, I first have to introduce Majoranas, why they're useful for quantum computation, why people are interested in them. And then I'm going to be introducing error-correcting codes based on Majoranas, why you would want to be thinking about those. And then finally, I'll introduce twist defects, which are going to be taking center stage in this talk. And finally, I'll see how much time I have, but hopefully I'll run you through some methods for computing with twist defects in the Majorana code, and importantly, show you why these objects are interesting in the Majorana context and why they sort of come with surprising features. Right, so to jump into the first part, so introducing Majoranas, just to start from the very basics, we've got fermions. So thinking of electrons in the condensed matter context, we also have holes, so sort of absences of electrons. And mathematically, they're associated with these operators, these fermionic creation and annihilation operators, with an anti-commutator that has certain special properties. And we can do a little trick with these operators. We can write them as with a real and imaginary part. So here I'm introducing these gamma operators, gamma 1 and gamma 2. They are self-adjoint operators. And at the moment, this is just a mathematical trick. There's no particular reason you would want to write your fermionic operators in this way. But it turns out that there are certain condensed matter systems that make this decomposition a sensible one to use. So specifically, what I'm going to think about is a chain of fermions. So we've got these fermionic sites. Each one can be occupied or unoccupied with an electron, say. And to each of these sites, I'm going to introduce two of these gamma operators. So these are the quote-unquote Majorana operators. And now in a normal system, we can imagine that perhaps the energy eigenstates are labeled by the occupation numbers of these sites, more or less. So, if I add an electron to one of these sites, the energy goes up a bit. But it turns out that unlike this very uninteresting system, this same system in a different regime displays some very interesting features. So specifically, if we add superconductivity, so if we add some superconducting coupling between these sites, we can pair up these Majoranas in a different way. So what do I mean by pairing up? So before, as I said, the sort of energy eigenstates were labeled by these the occupation numbers of these sites, and we construct these fermionic creation annihilation operators, these Cs, with Majoranas in the same site. So gamma J1 and gamma J2, which are located in that same site, that site J, those come together to form a fermionic operator. Whereas here, when we, in this different phase of this system, we label, we have energy eigenstates that are sort of roughly labeled by the occupation of modes that span different sites. So, okay, what does that mean? So I take these two Majoranas that are located, that are acting on sites, acting on these dots in different sites. So gamma J 2 and gamma J plus 1, 1. Excuse the confusing notation. And I construct these fermionic operators out of these two Majorana operators. And now, as you can see, this C now acts in between two different fermionic sites. So it's as if it's sort of creating a fermion or creating an electron that's sort of sitting between these two sites. It's sort of hopping between them. And when I pair up the Majoranas in this way, you can see at the ends of this chain, there are these unpaired Majoranas. So these operators that act on the ends of this chain commute with the Hamiltonian, and this makes them interesting for quantum computation. So let's explain this a little further. So at the ends of these sites, we have these Majoranas that, as I say, commute with the Hamiltonian. This means that they are zero modes, so we call them Majorana zero modes. It doesn't matter too much what that means, but what that results in is a delocalized fermionic mode. Okay, so what do I mean by that? So I take these two Majoranas located at the ends of the chain, And just as before, I construct a fermionic operator, a fermionic creation and annihilation operator out of these two Majoranas. So you can see here this C and C dagger, just as before, that creates or annihilates a fermion, but now that fermion is delocalized. It's sitting at the ends of my chain. So it's like the wave function of that electron is going to be, it's going to have some support on both ends of that chain. And that's a sort of very interesting feature in that it's why the Majorana, but this whole Majorana field is interesting for quantum computation. So if we sort of try and construct a qubit out of this, we can say, okay, well, if I have a state in which this delocalized mode is empty, it doesn't contain a fermion, then I'll call that the 0 state. And if it does contain a fermion, then I'll call that the 1 state. So it's sort of looking like we've got a qubit, we can start to do quantum computation. And just to note that these two states have the same energy. They both are pinned at 0 energy, at least in a perfect setup. And so, well, I'll talk about that a little later. So there's a slight caveat to what I just said. So it looked like we have a qubit that we've constructed from this Majorana, or from this chain of fermions. It actually is not quite that simple. We need 2 of these chains. And the reason is that to construct a qubit, we need to use basis states that have the same fermion parity. So what do I mean by that? So if I have 2 of these chains, I've got 4 Majoranas that I'm using for quantum computation. That means that I have 2 fermionic modes that could either be occupied or unoccupied. And you can see from the states that I've written here, so 0, 0, meaning both modes unoccupied, and 1, 1, meaning both modes occupied, they both have the same fermion parity, right? So an even number of fermions in both. And in that case, we can use these states to form the basis states, the computational basis states of a qubit. And this is for physical reasons. There's sort of no way that you can create a superposition of states with different fermion parities for sort of technical reasons. And the exciting thing about this type of qubit that I've just conjured up out of theoretical thin air is that certain types of errors are exponentially suppressed as you grow the size of this chain. So this is called topological protection of quantum information, and it's part of the reason why, despite this type of qubit being very, very difficult to realize in practice, people are expending a lot of effort to try and do so. There is another reason that this type of method of quantum computing is so exciting, and that's also because we can perform gates on this qubit that are also topologically protected. So as in the fidelity of this gate is very high, at least it can be sort of made arbitrarily high. So what do I mean? So if I exchange the position of gamma 2 and gamma 3, for example, if I sort of swap these positions, performing what's called a braid, then that the state undergoes some transformation. So if I started in the 0, 0 state, it gets mapped to this superposition of 0, 0 and 1, 1. And similarly, you can see how it affects the operators and the 1, 1 state as well. So this kind of looks like I've just implemented something similar to a Hadamard gate on my qubit. And that's exactly right. So that's what happens. So we by performing these braids, I can generate the single qubit Clifford gates acting on my qubit, and I can again do this in a way that is sort of as good as I like. I can get as good a fidelity as I like by performing this braid adiabatically. So this is the sort of, I guess, the pitch for Majorana qubits. But what about Majorana-based error correcting?
Just to slow you down for a quick second to make sure we all follow along. Can you say again a little bit more about the gamma 3 goes to negative gamma 2 and how you get the -2 in when you do this, and sort of what exactly the diagonal arrow means? Let's see in a slightly more physical picture.
Yeah, sure. So yes, this was a very schematic illustration of what I actually mean by exchanging the positions of these Majoranas. So in terms of a physical setup, it could be, well, there are a variety of different proposals for how to perform a braid like this. Maybe the most intuitive is that there will be some sort of network of these one-dimensional wires, and we can tune the position of where this Majorana sits by sort of tuning gates below these wires, and we can shuttle these Majoranas around the network, so that at the end of that shuttling, I've exchanged the position of two of these Majoranas. Now the minus sign is, so that is a result of the fact that these Majoranas behave as what are called non-abelian anyons. So that's to say that when you're sort of considering them as particles, they don't behave as fermions or as bosons. So if I exchange their position, instead of picking up a plus or minus one phase or for the wave function, what you can see here is that the wave function actually undergoes some non-trivial rotation. So these two states, 0, 0 and 1, 1, get sort of mixed together by the rotation. So if you go through if you go sort of from the Heisenberg picture of what happens to the operators to the Schrodinger picture of what happens to the states, this minus sign there, gamma 3 to minus gamma 2, results in this non-trivial rotation of the state.
Excellent. And maybe do you want to motivate for us? So if they were abelian, that would mean that they commute. The non-abelian part is important because
it means that we can actually perform gates by exchanging these positions. So if they were abelian anyons, then I exchange the position and the wave function picks up a phase, but that phase looks like e to the I theta, right? Where theta is just a number. And we all know that the overall phase of the wave function doesn't matter. So that's not very interesting for our purposes. It's interesting from a fundamental or condensed matter perspective, but we would like, to be able to perform gates.
Right. And maybe a final question before you move on. You've shown us how to do one type of gate here, but what can we say about universal computation of this picture?
Yeah, so you can, by braiding these Majoranas, you can achieve single qubit Clifford gates, assuming you sort of encode your qubits in the way that I'm illustrating here. So in order to get T gates, for example, if you want to go beyond the Clifford gate set, you can't do that in this nice topologically protected way. So you would need to supplement this with maybe magic states, which you've distilled out using magic state distillation, and to get C0 gates or some sort of entangling gate. Usually the proposal is to achieve that with measurements and ancillas. So it's sort of like this is the pitch. This is why people are kind of interested in it. But then there are a lot of caveats to that picture. So it would be very nice if we could get non-abelian anyons that have universal quantum computation that's achievable by just braiding them. But that's still a bit of an elusive thing.
Excellent. Thank you very much, Campbell.
No worries. So yeah, okay. So let's start talking about error correction with Majorana-based error correcting codes. So just to motivate this a little bit, why would we want to consider codes built out of Majoranas? So for on the one hand, you might say, well, say I want to compute with the surface code, for example. I want to use the best qubits available. If the promise of Majoranas ends up proving true, then Majoranas will be able to provide you with a very low physical error rate qubit. So you would potentially need to use a smaller distance code, have less overhead in terms of the number of qubits required to sort of encode a single logical qubit. Maybe you want to go from that direction. But then you might say, well, if I can get such low error rates, why don't I just use the qubits themselves as the logical qubits? Why do I need a code at all? And well, we've sort of discussed one reason. So one reason is that you can't get a universal gate set that is nicely protected like a braid is. The other reason is that there is a type of error which is not exponentially suppressed, as I mentioned, some of them were. So specifically what I'm talking about is something called quasi-particle poisoning, which is just a fancy way of saying take your state and apply a single Majorana operator to that state. So the reason that this comes with a fancy name is that this error sort of doesn't commute with the total fermion parity of the system. So it adds a fermion or it takes away a fermion. And this process is a sort of all or nothing thing. You can't kind of slowly rotate into this different fermion parity state. So it's I think there's some debate as to what the sort of rates of QPP will be in realistic setups, but it's a mechanism of error that you have to deal with. But just from a sort of fundamental perspective, it's interesting to sort of explore the range of codes that are available from any given building block. And in this particular case, we find features that you can't find in qubit-based codes. So yeah, there are no sort of analogs in the qubit-based world to some of the stuff that we're going to talk about. So that's a sort of from a sort of perspective of thinking of codes as objects of study in their own right, maybe beyond just what their use is for quantum computation. So they're models of condensed matter systems, for example. Okay, so I'm just going to dive into the main example that I'm going to be talking about, which is the Majorana surface code. So to define what this is, I've got this lattice here, this hexagonal lattice. It doesn't have to be a hexagonal lattice, but this is the example we're going with. And on the vertices of this lattice, I define or I locate the Majoranas that I'm going to be using for my code. And I'm going to introduce this group of Majorana, of 2n Majorana operators. So the group is just all possible products of these operators. And if you prefer thinking about Pauli operators, this is basically the same as the n-qubit Pauli group. Good, okay. Now there's an operator that we're going to, that is going to be very important, which is the total fermion parity operator for the entire system. So that's defined to be -1 if the fermion parity is odd, and 1 if it's even. And that turns out to be just the product of all of these Majorana operators up to a phase. Okay, and then to define the code, I'm going to define these operators OI, these plaquette operators. So for each of these hexagons, I just write down the product of all of these Majoranas around the boundary of this hexagon. And then the code, the states that this code encodes, I'm going to define to be the +1 eigenstates of all of these plaquette operators. So if you're familiar with stabilizer groups already, then this is exactly what I've just described. So the stabilizer of this code is generated by all of these plaquette operators. And the only difference between stabilizer in the Majorana context in the qubit-based context is that all of these members of my stabilizer group have to commute with the total fermion parity operator. And this is again this physical requirement that my encoded states all have the same fermion parity. So this requirement will come back later, and I'll be referring to it throughout. And so this is the Majorana. Oh, go ahead, Slavko.
And could you maybe tell us a little bit more about in what sense or just how far this equivalence or analogy between the Majorana 2n and the Pauli group can be taken?
So it's an isomorphism. So they are sort of the same group effectively, but the mapping is going to be very non-local. So this is where people start thinking about fermion qubit mappings. So this is, yeah, well, I mean, that's interesting from the perspective of if you have a quantum computer, how are you going to for example, simulate fermionic systems. But from our perspective, whatever is local in the physical Majorana setup may be something totally non-local in the qubit setup. So yeah, this is why you get sort of non-trivial things out of looking at these systems of Majoranas.
Okay, gotcha. And the Majorana operators, they either commute or anti-commute? Is that?
Oh, sorry, I might have forgotten to mention that. I apologize. So any two non-equivalent Majorana operators anti-commute. So that's required for the fermion operators, the Cs and C daggers, to have the right commutation relations.
Okay, great.
Yep. And then if you take one of these Majoranas and you square it, you get the identity.
Okay.
Also, something important to note is that these plaquette operators all have an even weight. So they, there are 6 Majoranas in these plaquette operators, and that is sufficient for this plaquette operator to commute with gamma total, so the total fermion parity operator. Again, I'll be bringing this back a bit later. So okay, so this is the sort of setup. Now, if you take one of these codes, you define some boundaries on this code in a particular way, like this. What you find is that there are logical operators that look like these strings that run between opposite boundaries, and these are going to be giving you the Pauli operators that act on your logical qubits that are stored in the code. So I've just defined, so I've sort of schematically illustrated what these operators look like. And you can also see there that this logical operator is just the product of all the Majoranas along this string. So that's sort of the Majorana service code defined. So what happens if we introduce errors into this code? Well, in order to sort of perform error correction with this code, as usual, what we do is we measure these plaquette operators, and if there's no error, then they all should produce the outcome +1. That was how the code space was defined, the space of codes of states that encode information. But if there has been an error, then some of them might be flipped to the -1 outcome. And so there are these errors sort of come in different flavors, right? So if I enact this gamma j, gamma k on my state, that anti-commutes with 2 red plaquette operators, as you can see here. And those are the ones that are going to be flipped when I perform a stabilizer measurement. So if I consider all of these even errors, so even parity errors, they all flip plaquettes of the same color. So I've shown red ones here, blue ones, and then there's this green one with the string sort of extending off ad infinitum. And that's going to be important when I define twist defects. So we think of these errors as, we think of these errors in certain contexts as particles in their own right. And I was talking about non-abelian anyons before. These flipped plaquettes can sort of move around the lattice as I kind of expand the error that acts on my state. And we can think of these flipped plaquettes to be anyons. They're actually abelian anyons. This is just sort of terminology, but I'm just explaining like what the language is that people tend to use when talking about this stuff. Okay, so and as I said before, there are 3 different types of these anyons or errors, which are colored the same as the 3 different colors of the plaquettes, and they're just colored the same as the plaquette that they sit on. So to define twist defects, maybe I should pause and just, are there any questions about the stuff that I've covered just so far, this errors and anyons and stuff?
Maybe not immediately question on this from the audience, but jumping one step back about, I guess, so from DPON, for the non-abelian anion chains, can a braiding of multiple such chains give rise to either fermionic or bosonic statistics?
I'm not entirely sure I understand the question. So, as in, if you have one of these chains, can you? Sorry, for the non-abelian anion chains.
Yeah, I think maybe take your best interpretation of the question, and Deepan, feel free to elaborate here.
Yeah.
If we've misunderstood.
So, in terms of the setup that I described, you will only find this non-abelian statistic like that. That's sort of part of that comes with the system, at least in the model that I was using. In terms of if you have a different system, remember all of this chain is solely made out of fermions with some particular interaction. So the non-abelian anion just sort of arises as this quasi-particle in my system. If you have a different coupling, a different setup, then you can find you would find quasi-particles that have fermionic or bosonic or different statistics. Yeah. Cool. So I realize I'm bombarding the audience with quite a lot of definitions and things, but I think this is my last one. So a twist defect is an object that can be very useful for fault-tolerant quantum computation in error-correcting codes, and specifically they're sort of put to use in surface codes built out of qubits for quantum computation. Yeah. Now to motivate why we would want to think about this, I think I talk about this a little bit later, but if we're interested in the variety of ways in which we can compute with Majorana surface codes, twist defects should be on the menu. That's something that we would argue. And they, so there are other proposed techniques for computing with the Majorana surface code, and in particular for performing Clifford gates on the logical qubits stored therein. But some of these proposals are somewhat inefficient, and so by exploring different methods, we could find more efficient, more low overhead methods for computing with this code. And as I'll show, by exploring twist defects, we actually find totally novel features that can't be found in bosonic or qubit-based codes. And specifically, we'll find a sort of doubling of the number of logical qubits that you might naively expect. And this helps sort of encode more information for less. So it's a sort of, another route towards lower overhead resource costs with this particular code. So so it's this, they are going to prove to have some interesting features. So let's sort of define them a little bit. So schematically, what I'm illustrating here is a pair of these anions, these flipped plaquettes. And in this particular case, they're both red plaquettes that are flipped. And the string between them is just the string of errors that anti-commutes with these two plaquettes. Now below that is a blue dashed line. So that's what is called a domain wall. Okay, what that is just it's a dislocation of the lattice. So it's a sort of physical change of the geometry of the lattice with a particular sort of finite extent. So it sort of just extends along a line and it can terminate at some point. And so those points at which the domain wall terminates, I've labeled with an X, and those are the twist defects that I'm referring to. And so how is this, what does this sort of dislocation do? Why is it interesting? So if I take two of these anions and I move one across the domain wall, that anion can flip change its character. So it can change from red to green, for example. And so that's sort of how they're defined. In terms of what they actually look like in the lattice, so here I'm illustrating a domain wall with this yellow dashed line, and the twist defects I'm just locating I'm indicating with these pink dots here. And so you can see everywhere else that I've sort of cut off from this picture on the left is the hexagonal lattice that I started with, and I've only changed this lattice along this yellow line here. And as you can see in the top right, I can find this string operator, this string of error, which flips a red plaquette at the top and a green plaquette at the bottom. So this is illustrating what I showed before, which was this process of if I move the red anion across this domain wall, it can change to a green anion. Good, and it turns out we can find a bunch of different types of these twist defects and domain walls in the Majorana surface code. So effectively, any permutation of these anion labels or colors that you can think of, there's an associated domain wall with that permutation. So in particular, we've got these ones that just swap two colors, so red to green, blue to green, and red to blue. And then there are also domain walls that sort of rotate between these colors, so red to green, then green to blue, blue to red, etc. And I label these Z2 or Z3 based on the order of this permutation. So if I can square this permutation, get back to the identity, that's a Z2 domain wall. Otherwise, if it has order 3, then it's a Z3 domain wall. And so, sort of unsurprisingly, these are all associated with the permutation group S3. And just to say that there's a sort of, these are just permutations of the anion label. So the Z2 ones just sort of flip 2 and keep the other one the same, and the Z3 one sort of rotates between these different anion colors. Okay, but the real interesting thing is coming from what I think of as twist defect subtypes. So each of these twist types that I had before permits 2 different subtypes. So as I've drawn here, you can see at the location of this twist, there is what I've tried to indicate as a hole. Okay, it's some sort of part of the lattice which has been kind of punched out. And to make this distinction between the subtypes seem more natural, I'm introducing some more Majoranas back into the lattice. So that's what these orange sort of pill-shaped shapes are referring or are indicating. So I've sort of glued some more Majoranas back down onto the lattice, and I'm pairing these up in a particular way so as to remove the degrees of freedom I've just added back to the lattice. So what that means is that I add some more operators to my stabilizer group, and those operators are given by these orange pill-shaped things here. So, but there's a different way that I could sort of pair up these extra Majoranas. I could instead pair up the sort of different adjacent Majoranas in this way. And if I do that, then I can combine the 5-sided hole on the left. So the 5-sided holes that are shown here, I can combine with the unpaired Majoranas at the end when I sort of repair them up, and I can combine that into a 6-sided plaquette. So sorry, I should have sort of had some ability to point to what Majoranas I'm talking about here. But hopefully you can see that if I just sort of change the pairing, I get an extra Majorana at the end of this line, and I can combine that with that 5-sided hole and just form a blue plaquette here. So sort of blurring over the details, what I've got here is effectively the same difference of, or the same transformation or phase transition as I had right at the beginning of this talk when I was talking about this chain of Majoranas and unpaired Majoranas appearing at the end of that chain. So the same transition between the sort of uninteresting and interesting case happens here, giving us two different twist subtypes. So I'm going to talk about a little bit more what I mean by this. But just to flag, what I'm calling these defect subtypes, these two twist subtypes are bosonic twists when they're in some sense uninteresting, and fermionic twists when they're in some sense interesting. So what do I mean by interesting? So as I said, that there are these sort of 5-sided holes that have been punched out at the location of the twist. So normally in a qubit-based code, in this code we can associate operators with these holes. So I can just sort of take the product of all of the Majoranas around this hole and call that epsilon A or epsilon B. Now, in a qubit-based code, you would normally associate some operator. You would take this operator and add it to the stabilizer group, and you can't do that in this case. The reason is that these operators, these epsilon A, epsilon B operators, they don't commute with the total fermion parity operator because they have odd weight. So as I said before, this is one of the requirements for being able to define a stabilizer group, is that all of the elements of that group had to commute with the total fermion parity operator. Because we can't do that in this case, they can't be added to the group. So, but we can notice that they do commute with all of the members of the stabilizer group. And so they begin to look a little bit like logical operators. So they're performing rotations within the space of code states. And indeed, that's kind of what they are, but we call them logical Majoranas because they obey the same algebra as individual Majoranas. So as I said before, individual Majoranas anti-commute, and so too do these logical Majoranas. They're also self-adjoint, so they square to 1, and so they behave exactly as Majoranas. So at one of these twist subtypes, what we find is an extra sort of degree of freedom, which is given by this logical Majorana. So, so what this is going to mean is that we have extra logical qubits that we can get sort of for free from our code. So to talk through these two sort of logical qubits, how do we think of these logical qubits? So on the one hand, you have the sort of uninteresting logical qubits in some sense. So on the left, I've got I'm illustrating fermionic twists with these blue circles because there's a sort of hole that's being punched out of the lattice. And on the right, I'm illustrating bosonic twists with these X marks again. Now, in both of these cases, I can find these operators, these strings that sort of encircle two or pairs of twists. And so this is what you expect to find in, for example, regular surface codes. So these are the sort of the qubits that you would expect to find in the Majorana case as well. So to distinguish them from what I'm going to introduce soon, I'm calling these bosonic logical qubits. And whenever you can find two of these string operators that anti-commute, you've got a logical Pauli X and Z operator that you can define, and so you know that you've got a logical qubit that your code is storing. So okay, we've got this one type of logical qubit, but we've also got just for completeness, we've also, as I said before, we've got Z2 and Z3 twist types. And in the Z3 case, we have a slightly more complicated looking set of operators that we can define. And in fact, this encodes two logical qubits among two logical qubits among 4 twists, as opposed to one logical qubit among 4 twists. Okay, but the main take home is that when we have fermionic twists, we also can find these logical Majoranas located at these twist sites. And if I multiply a pair of these logical Majoranas together, I get I get a logical operator. So this X or Z logical operator acting on some of the degrees of freedom of my code. So there's this sort of extra logical qubit, which is the fermionic logical qubit, to distinguish from bosonic logical qubits, which is only sort of achievable in Majorana type codes. So this is the sort of doubling thing that I was talking about before. And just to say that you can't, just as before, you can't use one of these logical Majoranas by itself to have to encode a qubit, because, well, it was for the same reason that you couldn't you couldn't have a single chain of a single fermion chain with 2 Majoranas and encode a single qubit in that, so that the fermion parity didn't work out. So we need 4 twists and 4 logical Majoranas to give us a fermionic logical qubit. Okay, so just to showcase these two types side by side, what are the differences between these two types of logical qubits? Well, on the one hand, the bosonic logical qubits, as in most codes, if you increase the sort of size of your code, the code distance, you increase the weight or the minimum weight of logical operators, and thereby incur sort of better protection of your information. For the fermionic logical qubits, they are sort of protected by a variety of different mechanisms. So one is the code distance. So it's sort of a moderate code distance, let's say. And so that's, again, the minimum weight of these logical operators. But they were also partly protected by the fermion parity conservation of my physical system. So if these QPP errors I mentioned a while ago, these fermion parity odd errors are suitably rare, then I don't need to use as much code distance to protect my logical qubits by the same amount. I'm sort of using that low probability in my favor here. But to protect them, I need to still move these twists far apart so that there aren't fermion parity even errors that can cause an error. So this sort of combination of factors protects my fermionic logical qubits. Okay, but then how do we actually compute with these two different qubit types that we find in Majorana codes? So I'm just sort of going to highlight some various methods for doing this, and thereby sort of show some of the advantages, I guess, of looking at twists. So as I mentioned before, there are sort of for performing Clifford gates on qubits, there are some sort of somewhat less efficient methods that are proposed in the literature, involving sort of ancillas and state distillation steps. So here, when we have twists, we can actually perform all the Clifford gates that we like on our bosonic qubits by braiding or exchanging the positions of these twists, which you can do through measurement-based procedures. You can also do it through lattice surgery, which I'll talk about a bit later if you're familiar with lattice surgery. But just to sort of talk through how you kind of reason about this. So if we take 4 twists, like I've done here, and we've got these 2 logical operators that we can define with these twists. If I then exchange the position of twist 3 and twist 4, like I've done on the right here, you can sort of track how that changes the logical operators. And so just to talk through this a little bit, if I've sort of using the properties of these logical operators and how you can combine strings together in a certain way to track what happens. So in this case, I've sort of created this little bubble around twist 4 as I kind of move it, push it through this logical operator. And if I take a green and a blue string, just by the way, you can sort of zip it together. Sorry, a green and a red string, you can kind of zip it together into a blue string. This is what is shown there in that right-hand panel. I'm not expecting this to immediately make sense. It's just an illustration of what the how you can reason about this stuff. Yep. So and if you use your imagination, you can sort of imagine going from the left to the right-hand panel, and then as I keep on doing this exchange, we can then unzip this blue string again into the red and the green strings in this particular way. So this is showing how the Z operator goes to a product of Z and X operators, or in other words, it goes to a Y logical operator. And you can also see that the X logical operator is not going to be affected by this braid. So this is to say that this appears as a single qubit Clifford gate on my encoded information. And to get more complicated gates, so to get the entangling gates, like the C0, for example, you can take these Z3 qubits, Z3 twists, that I mentioned earlier, and these 2 logical qubits that are stored in these Z3 twists. And you can, by braiding, by performing this braid that I'm indicating here, so taking the bottom left-hand twist and sort of moving it around the top pair, you can sort of see what happens when you do this twist, and what you get is a sort of string of transformations of your logical operators, which means that the Clifford circuit you're implementing entangles these 2 qubits. Now, just if you're following this panel on the right, so the 3 sort of panels here, the only non-trivial step is going from the 2nd to the 3rd panel there. So what I'm doing is I've got this loop of domain wall that goes around the top pair of qubits, of twists, sorry, using the wrong words all the time. And all I'm doing is I'm just pinching off this domain wall below the two twists, the top two twists. And what that gets me is a loop of domain wall that goes around the top two twists. And then you need to use the fact that you can actually just define away a domain wall. It's what's called gauge dependent. So I can sort of delete a loop of domain wall at will by just relabeling the colors of the plaquettes. So this is something that we go through in the paper, but it's the result of that is just to recolor the string operators, and so we get from this blue string operator to a red string operator like that, and that takes us from x1 to x2. Good. So yeah, and if you do this with all of the other operators, you find this transformation here. So all of that is to give a bit of a flavor for showing how the twist, braiding these twists can get you any Clifford gate you like on encoded logical information for the bosonic qubits. So what about the fermionic qubits? So if I take one of these twists that hosts a logical Majorana like this, I'm going to use what's called lattice surgery to perform a Clifford gate on this on some fermionic logical qubit. So to do this, I'm first going to enlarge this twist a little bit. So I'm going to sort of expand it, expand the hole located at this twist. And then I'm going to take it towards this, towards an external boundary in the lattice, and just sort of merge it with that external boundary like that. And if I flatten things out a bit, we get this. We've sort of smeared out this this twist into this external boundary. And so when the logical Majorana was initially located at a twist, it's now sort of again smeared out across this whole boundary here. And the thing to note about this external boundary is that it will have an odd length because the logical Majorana has to have odd weight. So the boundary that supports that Majorana, that logical Majorana, will have odd length. Okay, now that it's located on a boundary, I can do lattice surgery. So what is lattice surgery? Well, given two or more of these logical Majoranas, I might want to perform measurements of an operator like this, so I epsilon A, epsilon B. And if I can perform measurements of this or of any product of 4 or 6 or 8 logical Majoranas, for example, and I can prepare some ancillas, then I can perform any Clifford gate on the fermionic qubits in my system. So how does this actually work? So this is the reason that why I would want to measure an operator like this. In order to, I would measure it to perform a Clifford gate on my fermionic qubits. So how do I actually measure it? Well, to measure it, I introduce an ancilla patch, including a bunch of Majoranas here. So this bottom section here is a patch that's introduced just to perform the measurement. And that ancilla patch hosts 2 logical Majoranas, so epsilon A tilde and epsilon B tilde. And on the right here, I'm sort of indicating schematically what's going on. So in the beginning, I had these 2 logical Majoranas that sort of came from 2 twists. And there's some eigenvalue of this operator lambda that I want to measure. And now I prepare this ancilla patch as well. And this ancilla patch will be in a fixed parity sector. So it's going to have another operator I epsilon A tilde, epsilon B tilde, and that's going to be evaluated to +1 on the state that I prepare. And then I just fuse these patches together at the locations of the logical Majoranas. And this is sort of how lattice surgery works in general. But this, if you're familiar with lattice surgery in the surface code context, for example, this has some differences because the surgery measurements that I perform don't commute with the operator that I actually want to measure. So they have a slightly different interpretation. Effectively, so when I surger these 2 patches together at the first location, you can think of that process, that measurement, as teleporting the operator to measure to lie between two different logical Majoranas. So I've sort of taken this this initial setup here with the operator I want to measure and the ancilla operator, and I kind of rotate them, rotate this whole system. So now this is the operator I want to measure, and this is the one that I just have measured. So I do a teleportation type of measurement. And so then when I do the second surgery measurement, then I get the eigenvalue that I wanted to measure out of that, out of those two measurements. So if this is not making too much sense, that's okay. I don't know what people's background is. It's just to say that we do this particular measurement-based procedure in order to perform these Clifford gates. And then just to get back to where we started, we just sort of destructively measure the ancilla patch, and that sort of projects me back into the state in which I measured I was, potentially up to a correction operator that I have to track. So that's sort of talking through a particular example of this protocol, and it generalizes quite nicely. So any arbitrary product of logical Majoranas I'm able to measure. So that means I can perform any Clifford gate that I would like. And in particular, I can actually perform Clifford gates using something very similar, a very similar protocol between bosonic and fermionic logical qubits. So I have these logical qubits that can encode information side by side, but it turns out I can also compute with them together in a parallel fashion. So I can entangle them, and then I can perform a circuit on the entire set of logical qubits that I have at my disposal. And yeah, so that's the sort of take home. So this is, I've just been talking about Clifford gates so far. Again, we need to supplement that with T gates, as we were sort of talking about a little while ago. So how do we do that? Well, the general way of doing this is by injecting magic states into your code somehow. Magic states being ancillas that you can use to sort of inject a T gate into your circuit using Clifford gates and measurements. So the way that we do that in this code is by taking 4 qubits. Sorry, I'm doing this again. 4 twists. And this is going to be encoding, these 4 twists are going to encode bosonic and fermionic logical qubits. Then I bring 2 of the twists together so that they have sort of minimum separation. And then I apply some rotation gate to the Majoranas that make up the code. And I assume that I'm able to do that. I assume I'm only able to do a noisy copy of that rotation gate, but that's sufficient because I can sort of combine this with magic state distillation to improve the copy of the magic state that I have at my disposal. And so this is an example setup for how this works. So I'm just showing the 2 sort of top twists here. I bring them really close together. And what you can see is that they have sort of expanded a little bit from the initial picture that I was using. This just provides a bit more added protection for the the logical information. And then when I perform this gate this pion 8 gate involving gamma 1, gamma 2, then that prepares the magic state that I want to prepare. So then that sort of completes the gate set, and I can now sort of perform any gate I want in my Majorana surface code. In terms of, I'll sort of briefly talk a little bit later about overheads and why, I sort of already mentioned that this gets you some more qubits for free, but we can also sort of use these logical Majoranas to restrict the number of Majoranas that you need in general in your code, and sort of get lower overheads for computing with this code. Okay, but before I do that, there's just a bit of an aside. There's a different way that you can achieve Clifford gates with this code, which really uses the non-abelian nature of the Majoranas that are making up the code. So it's really, it's sort of most easily illustrated with a small patch of Majorana surface code. So if I take this patch here, it's just a small number of Majoranas that are making up this patch. And if I take Majoranas defined on sort of opposite ends of this dashed line here, and I braid them with one another. So again, this is, I mentioned right up the top that you can sort of exchange the locations of Majoranas and get a gate out of that. So if I perform this braid that sort of maps between, or that braids all of these Majoranas on opposite sides of this this dashed line, that actually preserves the stabilizer group, and so it's an encoded gate, and the gate that it actually performs is something similar to a Hadamard gate. So it's a Hadamard times the logical X operator. So I've just defined the logical X and logical Z operators for this code here with these loops. So this is kind of interesting from, I guess, from the perspective of transversal gates, because in a general qubit-based code, you want to find gates that you can perform in such a way that they are fault tolerant. So if I have some error that occurs on my system, perform the gate, I don't want that gate to then spread the error over a larger area in my code. And that's one of the features of that's why you would want to use what's called a transversal gate. So transversal gate has this sort of locality of error preserving feature. And now in this case, we've got this sort of fermionic or Majorana based analog of a transversal gate, which is this sort of long range braid between different Majoranas of my code. And you can find this type of gate whenever you have a line of symmetry in the lattice of your code, because this dashed line is a line of symmetry, right? A mirror symmetry, and I can just sort of shuffle all of the Majoranas around across this line. So if I find codes with sort of more complex looking lines of symmetry, then I can get more complex looking Clifford gates out of this procedure. So in this particular case here, I've got like 2 lines of symmetry, and that means that I've got 2 different gates that are achievable by braiding across these lines of symmetry. So it's not too important what these circuits are, and what, it's just to say that there are these 2 Clifford gates that you can get out from these 2 braids. But what's interesting is that this isn't really non-analogous to anything you can find in a qubit-based setup, because if you just imagine a qubit-based code and you perform some swaps across the line of symmetry in the qubit-based code, you'll find that you might get a Clifford gate out of that, but if you square that, you'll get back to the identity, right? If you square a swap gate, you'll get the identity, and so that sort of limits the Clifford gates that you can actually find from this procedure. Whereas because these are non-abelian anyons, these Majoranas are non-abelian anyons, when I square this braid gate, I don't get the identity, I get a logical Pauli. That's what I'm showing here. So this UL is the braid that goes across this line of symmetry. When I square that, I get a logical Pauli operator. And so this is just to point out that there's this mechanism for performing gates that gets you very different results from what you would expect by looking at a qubit-based code. And you can also achieve a sort of greater fraction of the total Clifford gate set that by doing this. So it's a sort of in near-term codes, if we get a handful of Majoranas and we want to prepare a code with this handful of Majoranas, this is a way that you could perform logic gates on these codes in near-term devices. I say near-term, I mean Majorana qubits are in general further down, like a further distance in the future than any other type of qubit. So near-term has a relative meaning here.
Yeah, and I guess right as we get to the end of your talk, that's probably where a lot of questions are going to come up, or I've seen in the chat around, as we're coming over the hour here, around the connection to hardware and so on. But I'll let you get to your conclusion slide first.
Yeah. So I'm basically finished now. I just want to signpost. Yeah, this is just some basically saying what I had before. I just want to signpost that, as I said before, you can find some sort of reduction in overheads by looking at these logical Majoranas. So I'm just sort of showing here a kind of example setup where the ancilla patch that you use for measurements can be sort of squished to reduce the number of Majoranas that you need. But I won't go into detail there because, as you say, we've run over the hour. I think future directions I can probably just sort of come back to later if there are questions about that. But just to summarize very quickly. So as I mentioned, as I have pointed out, in the Majorana surface code, and indeed in Majorana codes in general, twist defects have this nice sort of dual feature where you can find fermionic and bosonic flavors. And one of these hosts logical Majoranas, which means that you get sort of two different types of logical qubits, and you can compute with these two qubits in parallel. And so this sort of opens up new methods for computing with Majorana-based codes, and in particular, you might, in particular, some lower overhead methods for performing computation with these. So that's the summary. Yeah.
Thank you very much, Campbell, for the very nice talk. Folks, this is a great time to post your final questions here as we come up on the next few minutes of questions. There were, as I alluded to, and as you alluded to yourself, there were a lot of questions around implementations and hardware, and how close is the theory to where things are? What are the current rates or anticipated rates? Maybe we can start with that.
Yeah, so as the audience might be aware, a few years ago there was a sort of reproducibility crisis within the Majorana field, and it was all a little bit unfortunate, I would say. I think it's so from my read, and I interact with the experimental literature much less than anything else, or than the theoretical literature, but my understanding is that we're still sort of in the phase of proof of concept. So as in proving that you have Majoranas there at all. And so the majority of the experiments, in fact, I think all of the successful experiments, if you take them at their word, have shown the existence of these Majoranas through what are called zero bias conductance peaks. So basically showing that there's this zero energy mode that an electron can hop into and hop out of. And it's very difficult to, my understanding again, is that it's very difficult to distinguish between when that is a signature for a real Majorana pair that is existing in your wire and when it's some spurious non-topological effect that you're finding. So it's a really difficult experimental problem. So all of the stuff that I'm saying here is certainly much further down the track in terms of implementation than looking at qubit-based surface codes. And in terms of what the setups are actually going to look like, I mean, there's a very different. Most people are considering some networks of wires or collections of wires, each containing a pair of Majoranas. But I should flag post that there is a very different setup proposed, which is sort of more appropriate for things that I'm thinking about here, involving a what's called a topological insulator, a sort of it's a 3D one, so it has a bulk which is insulating, and then a 2D sort of surface which conducts current on the boundary. And when you have this, you sort of imprint some superconductors on top of this topological insulator. And When you do this, what you find is that the superconductivity sort of bleeds into the surface of that topological insulator, and it picks up some special properties which are needed to find Majoranas. So you can sort of imprint this. You can imprint this network of Majoranas in sort of any shape that you would like, and kind of create this 2D grid in this hexagonal shape that we're needing for this surface code. So that's like a very different proposal for how to achieve this type of code.
Great, and there's probably actually more questions than we have time to get to, because we'll have to end here in a minute or two. But maybe two quick questions. One is, for folks who are familiar with mathematics and coding superconducting-based qubits, but want to learn more about the topological world and circuit breaking math, what resources would you like to point to?
Yeah, so that's a good question. So I mean, there's a very nice review on topological quantum computing in general. I would just have to remind myself of the authors of that. I think it's Chetan Nayak and Ben Simons. So I would need to double check the authors there, but I don't know. Is there a way of leaving it in the comments, or?
I believe Paul, our producer here, will be able to update and do that for you folks, and we can post it in the video description.
Yeah, and sorry, Steve Simon. Yeah, thanks, Paul. Steve Simon, not Ben Simons. Sorry, and Steve Simon also has a nice set of lecture notes on all things topological in the quantum world. So yeah, those are some go-to ones.
Okay, great. And let's see if we have time for one quick final question here.
Sorry if I bled the time a little bit and didn't leave too much time for questions. Apologies for that.
That's quite all right. Maybe 2 sentences on fermionic twist versus bosonic twist and how they're different.
Yeah, so a little summary on that. So effectively, the fermionic twists allow for you to or host logical Majoranas. So they have this sort of extra sort of degree of freedom associated with them. The bosonic twists don't. We've sort of like defined them away by changing up the way we've defined these twists. Yeah.
Excellent, great. Well, Campbell, with that, thank you so much for the wonderful talk. There's some very nice comments in the chat. Folks, you've been awesome and active as always. So thank you very much for keeping it busy for me during the presentation here with lots of stuff in the chat. I think with that, Campbell, the music.
Thank you very much. Yeah, well, thanks for having me. This is really nice.
Yeah, it's last. What is that song that they always play at the end of the night? Last. Forget what it's called. Well, anyway, with that, folks, we will see you next Friday at noon Eastern time. I'll be on vacation, so it won't be me, but we'll be here.
Great.